A very good morning to all of you. I cordially welcome you all for this applied thermodynamics course. So, in the today's class, we are discussing about lecture number 3, that is the CDT 3. The topic is representation of various processes on the Mollier diagram. So, in this particular class, we are able to know how can we represent the various processes on the Mollier diagram, because I've already told you that the Mollier chart is nothing but representation of the HS diagram, that is the enthalpy versus entropy diagram. So on this particular Mollier diagram, how can we plot the various processes, means constant volume, constant pressure, isothermal, adiabatic and polytropic processes? How can you represent it on the Mollier chart to find out the performance of the thermal power plant? So at the completion of this particular lecture, I am expecting every student should be in a position to evaluate the properties of the steam from Mollier chart to find the performance of the thermal power plant under the given conditions. So I've already told you that the how can you represent the Mollier diagram, that is the HS line. So this is the saturation line. So here you are able to have the X value is equivalent to 1 on the saturation line. So similarly, so this is the representation of the constant pressure lines. So these are the constant pressure lines. And similarly here, the curved lines towards downward direction. Now these are representing the constant temperature lines in the superheated region. Now it is in the liquid region, and now it is in the wet region. So these are the various dryness fraction lines you are able to observe on the HS diagram. So the Mollier diagram is basically having the various types of the lines, starting with the dryness fraction lines, constant value, constant pressure, constant temperature, constant entropy, and constant enthalpy, which is also known as is a throttling process. Now, the basic theme of this particular today's class is how can you represent the various thermodynamic processes of vapor on the Mollier diagram. So since there are several processes are there, so today's class is restricted to only 2 or 3 processes only. So that's why let us discuss only the constant volume process and constant pressure process representation on the Mollier diagram in the today's class of the CTT. So before going to that, let us solve one problem, that is to familiarize with the usage of the Mollier chart. Just I will given you the fundamental problem based upon the Mollier chart. So please go through the problem. So using Mollier chart, find enthalpy drop and final condition of the steam when it is expanded isentropically from an initial pressure of the 30 bar and 350 degrees centigrade to a pressure of 1 bar. That is, he is saying that the expansion process is taking place according to the isentropic process. That is, the entropy parameter remains constant during the process. So write down the given conditions. So that is, the initial pressure is given as 30 bar, P1 is equal to 30 bar, and T1 is equal to 350 degrees centigrade, and isentropic expansion is taking place to 1 bar, that is the P2 is equal to 1 bar. So now all of you please go to your Mollier chart, which is there on the steam tables. So take your pencil, scale. So now P1 is equivalent to 30 bar. So go to the Mollier chart. So identify the 30 bar line. So let us say that this is my 30 bar line is passing like this. And T1 is equivalent to 350 degrees. That is, first of all, your duty to identify what is the type of the steam, whether it is a wet steam or dry steam or superheated steam. So now you identify what is the initial condition of the steam. So it is on 30 degrees. And here the constant temperature line is passing like this. So it is a constant pressure of the 30 bar is passing like this. Both are intersecting at this particular common point. So this common point is represented as point number A. So now from this particular point number A, what is the process? It is the isentropic expansion process, that is constant entropy. So you know that constant entropy lines are represented by drawing a vertical line. So that's why from point number A, now just you draw a vertical line, till up to what point, that is he has given the final pressure is equivalent to 1 bar. So now this is the 1 bar line. So this is the 1 bar line is passing like this. So wherever this 1 bar line and this isentropic process, whenever both are intersecting with each other, now you identify this particular point as B. So now from this particular the point number B, we came to know that so it is falling in the wet region. So the outcome is nothing but is a wet stream. So we have to find out what is the dryness fraction. So through this particular the point number B, which dryness fraction line is passing. So this is the dryness fraction line which is exactly parallel to the saturation line. So that is we came to know that the x is equivalent to 0.9, that is the 0.9 dryness fraction line is passing through this particular point number B. So that's why the point B dryness fraction is equivalent to 0.9. Now he is asking us to find out what is the enthalpy drop. So from this particular the point number A, draw a horizontal line. So this is nothing but HA. So HA value is equivalent to 3120 kilojoules per kg. And similarly from point number B also draw a horizontal line. So that is giving you HB. So HB is equivalent to 2450. So these are the values we are able to obtain from the Mollier chart. And enthalpy drop, that is the higher value minus the lower value. So that's why it is 670 kilojoules per kg. That is the enthalpy drop. And similarly is also asking about the final condition of the steam. That is the X is equivalent to 0.9. That is the wet steam is basically leaving. So like this you can solve the basic problems of the Mollier chart. Now similarly, you can also go through the next problem. The next problem is also given in this particular one. So he has given the T1 is equivalent to is a 200 degrees centigrade. So T1 is equivalent to 200. So the initial pressure P1 is equivalent to 7 bar and constant enthalpy process is taking place. P2 is equivalent to 3 bar and next one it is P3 is equivalent to 0.5 bar. So from this particular one, now go to the Mollier chart. So go to the Mollier chart. So first of all, locate the point number A. So locate the point number A. That is, it is the 7 bar. So it is a 7 bar line is passing like this. And the 200 degree centigrade is a 200 degree centigrade and it is a 7 bar line. So both are intersecting at this particular point. So it is my point number A. And is saying that is a isenthalpic expansion. That is a constant enthalpy expansion process is taking place. That's why from point number A, so draw a horizontal line. So this is representing H is equivalent to constant. So this horizontal line is to draw because it is expanding up to 3 bar. So it is a 3 bar line. So this horizontal line and this 3 bar line both are intersecting at point number B. So HA is equivalent to HB because it is a throttling process. So from the Mollier diagram we are able to know that so it is 2850 and similarly also find out what are the entropy values at the point number A and at point number B. So SA is equivalent to 6.84 and here SB is equivalent to SC because it's a constant entropy expansion process is taking place. So here it is 7.24. Now, after locating the point number B, next he is saying that is an isentropic expansion process is taking place till it reaches the 0.5 bar. So it is a 0.5 bar line is passing like this and is the isentropic process, that is a vertical line. So both are intersecting at this particular common point, point number C. So at point number C, find out what is the value of the HC, that is 2535 kilojoules per kg. Now what is the first bit is asking what is the change of the entropy. So change of the entropy means nothing but is the SB minus SA because SB is equivalent to SC. So SB minus SA. So the answer is 0.4 kilojoules per kg. And change of enthalpy. Change of enthalpy during the constant enthalpy process. So because HA is equivalent to HB, so automatically there is no change. So the answer will be equivalent to 0. Next he is asking during the constant entropy process, what is the change of the entropy? Because SB is equivalent to SC. So SC minus SB will be equivalent to 0. And similarly the change of enthalpy, so that will be equivalent to HB minus HC. So that will be equivalent to 315 kilojoules per kg. So like this you are able to solve the problem. That is here both the processes combination is given, that is a constant enthalpy as well as the constant value. So both are given in this particular one. So now let us discuss about the important one, that is how can we represent the constant value process on this particular the Mollier diagram. So because we already studied, that is how can we find out the specific value of the wet steam as well as the dry steam as well as the superheated steam. So already we're using the similar formulas. Now we can find out what is the value of the X if it is the wet steam, and if it is a dry steam, so it will be equal. And if it is the superheated steam, by using the Charles law, we are able to find out this particular one. And the next one, the work done, because the work done during the constant volume process, that it is equal to P into dV. So change in the volume is equal to 0. So automatically the work is equal to 0. And similarly, how can we find out the internal energy? Because H is equal to U plus PV. So from this, we are able to write down the U is equal to the H minus PV, is because the conversion of the factors, because the PV to, because here we are representing in the kilojoules per kg, so that's why we are multiplying with 100 to get the units in kilojoules per kg. So if the V1, it is the wet steam, so V1 is equal to X1 into Vg1. So for that particular one, we are able to find out the H2 minus 100 P2 X2 Vg2. That is the formula for the wet steam. And for the dry steam, X2 is equal to 1. So it is a P2 into Vg2. And for the superheated steam, it will be V superheated. So the change in the internal energy is nothing but du is equal to U2 minus U1. And how can we find out the delta Q? So from the first law of thermodynamics, delta Q is equal to du plus delta W. And here the delta W is equal to 0. So that's why delta Q is equal to du. So like that, we are able to have the constant value process. Now let us see one problem on this particular one, that is the constant value process. So please go through the problem and write down the given data. So the given data is given, that is what is the value of the V, P1, X1, P2, X2, P3, all those things. So now let us find out first of all what is the initial mass of the steam in the vessel. That is V is equal to M1 into X1 into Vg1, because it is the wet steam is there. So from this particular one, find out what is the value of the M1. So M1 will be equal to 2.33 kgs. And similarly, find out what is the value of the total internal energy, the U1 formula, because you know the U1, because initial condition of the steam is nothing but wet steam. So H1 formula will be equal to HF1 plus X1 into HFG1. And similarly, you also substitute what are the values of X1 and Vg1 from the steam tables or from the Mollier diagram. So we are able to find out what is the value of the U1. And similarly, the final mass of the steam after mixing is always equal to M1 plus M2. So already you know what is the value of the M1, you substitute here. So M3 will be equal to 2.33 plus M2. And similarly here, the total volume of the steam, so this will be equal to, that is a V total. So V total, this is always equal to, it is the M3 into X3 into Vg3. So from this we are writing down the formula of M3. So M3 will be equal to 2.33 plus M2 is equal to, what is the value of this particular one? That is 1.2 divided by X3 into Vg3. So from this we are able to write down the X3 value and here the U3 value, and here we are able to find out the M2 value will be equal to 1.167 kgs by substituting all the values in this particular formula. So totally by substituting all the values, we are able to find out the final dryness fraction of the steam in the vessel. It is X3 is equal to 0.917. That is, the wet steam is basically leaving the vessel. That is the final condition of the steam. So based on this, you should be in a position to answer some of the important objective type of the questions. So just I have given you some important questions which were asked in the previous GATE and IES examination. So now try to solve these particular questions. So just you write down for first bit what is the answer. Later you check with the correct answer. Just I am giving you the right answers also. Just you compare whether are you in a position to get minimum 60% of the marks or not. Just you will check. If you get minimum 60% of the marks, okay, satisfactory. Otherwise, just you have to concentrate more on this particular, the fundamentals of this important lecture. So these are the answers for the given question. So in the today's class, we are basically restricted to the constant volume process representation on the Mollier chart. So in the next class, we will discuss about some more process representation on the Mollier diagram. So thank you one and all for listening this important lecture on constant volume process representation on the Mollier chart. Thank you.